Here's the problem. An astronaut becomes stranded in space at the radius of Jupiter's orbit away from the Sun. But instead of our Sun, it's a black hole of the same mass. The astronaut starts from rest and begins slowly drifting into the black hole purely radially, and is doomed to eventually hit the event horizon and never come back. Fortunately, our astronaut packed their prized bowling ball. The question is, assuming the astronaut can survive indefinitely in her suit, can the astronaut escape their doom of plunging into the black hole's event horizon? Let me know what you think and why in the comments below. The answer here is yes. You may think that since she starts from rest, she could throw the bowling ball towards the black hole and by conservation of momentum, she moves away from the black hole. However, for a standard throw speed of bowling balls, the gain in velocity is only about 2.3 meters per second. The escape velocity needed for our black hole is the same as the escape velocity of the solar system at Jupiter's orbital radius, since the Sun and the black hole have the same mass. This is about 18.5 kilometers per second, which is much faster. So eventually she will turn around and go back to plunging into the black hole radially. Instead, she can throw the bowling ball sideways and give herself some angular momentum relative to the black hole. The entire reason that Earth orbits is because our planet has enough angular momentum that despite falling into the Sun due to gravity, it keeps missing. To visualize, here's a plot of the effective potential of a black hole. The height corresponds to a kind of barrier called a centrifugal barrier, that a particle with a particular energy can either cross or not. The height of the barrier depends on the angular momentum. For a black hole, this barrier has a finite width, but in classical mechanics, any tiny amount of angular momentum causes the centrifugal barrier. In the case of relativistic orbital mechanics, which our astronaut has taken a class in, if we increase our angular momentum, we can raise the centrifugal barrier and bounce back, outward, and miss the event horizon. Thus, she throws the bowling ball to her side, and by conservation of angular momentum, assuming she has a heck of a throw, makes the resulting geodesic of our astronaut have a periapsis, or closest approach to the black hole, about 4 kilometers away from the event horizon. Unfortunately, this is still too close, and the tidal forces will cause the gravity on her feet and the gravity on her head to pull at such different strengths that our poor astronaut will spaghettify. But we'll just have to wait until the next physics problem to address that.